Swayam Prabha, free DTH channel for education.
Okay, let me also share the screen now. Hope the screen is visible to you now. Okay, let me ask you a question here. Anyway, I don't want to again go through it in the same way as we have, that's anyway is covered in the video lecture, and I'm sure most of you have watched it. So let me put you a question here, particularly on this slide. Let me see if I could put it here, right. Ignore about this negative transform. Okay, ignore about this part and take a look at all the remaining transforms. So essentially on the x-axis you have the input intensity values, on the y-axis you have the output intensity values to which they are getting mapped to, right? Now mathematically, suppose if I come up with a another transform curve, what is the properties that you would be looking, or what is the properties that you think that it should have, this transformation curve should have? Is the question clear? As I mentioned, ignore about the negative one. So there is inherently there is one property followed by the rest of the transformations. So can you formalize that and say what could be the property, desirable property, while you are coming up with a transform that maps the existing intensities to new set of intensity values?
Same range of values.
Same range of values. I would say not always necessary, because of course in this curve you are right actually. Suppose if you are going to use the same data type, yeah, what you said is most of the times correct. Agree. Any other property?
All of them have.
Monotonous.
Sorry.
Should be monotonous.
Very good. Right, very good. Who is that? Muhammad or Pranjal? Right. That should be monotonous. What if it is not monotonous?
If it's not monotonous, we will get the intensity at some point to be higher. If we compare the intensity between two pixels, the intensity which would have been lower in the erstwhile image would come
Right.
out to be higher in the real image. So that would be a
Right.
problem.
Very good. Correct. That's the very, very important property we need to look at while you are looking at any transform. Otherwise, what would happen is now intensities have an interpretation here, right? As you have seen in the X-ray images, there is intensities, for example, there if the absorption is more by the object. So then you have a high intensity or low intensity there on the screen. You have a absorption is more by a particular the ray coming on the way, there is an absorption is more. So what would happen to what you get on the film? High intensity, right? So here intensity has an interpretation. So while you are mapping it, it's not like the intensity ranges should get flipped. Okay, then the whole thing is lost. Very good. So the next one, should it be strictly monotonous, or let me put it this way, what happens when it is strictly monotonous, and what happens when it is just monotonous, not strictly monotonous? I hope everyone is clear with what it means by strictly monotonous and normally monotonous. If not, I would just show you this curve here. Okay, see this curve here. So for example, here is where the intensity, this is your input intensities, output intensities. This curve is giving you the mapping, right? Is it strictly monotonous or just monotonous?
Just monotonous.
Right. Like how do you say that and what property here?
Because it's non-increasing. Sorry,
Correct.
non-decreasing.
Right. So yeah, it is remaining same for multiple values while you are, it is not increasing but never decreasing. So that's what a strictly monotonous. So this is just monotonous. Strictly monotonous means something you have like this, right? So what would be the implications when you have a curve which is strictly monotonous and simple monotonous?
In simple monotonous, many values will get mapped to the same value.
Right,
And the
that's
vice
right.
versa also.
Right. So what would be the implication of it? Can you think of any implication of it?
The implication would be that we won't be able to differentiate certain pixels, certain intensities and pixels for that matter in the medium.
Yeah, that's right.
The differentiation will be lost.
Correct. So can you tell anything about, I agree with the answer. So let me slightly change the question. It's like, suppose, what could you say about the inverse transformation? Now that being monotonous or strictly monotonous, what can you say about the inverse transformation? Is it clear by inverse transformation what I mean by, suppose I would like to start from here and get back here.
Those not exists in that those cases. Those can't
Right.
exist in those cases.
Yes. So as you could see here, when so it is very clear here where a given intensity value would get mapped to. That would be clear even when it is normally monotonous. But the moment it is, you want to come back, unless this function is strictly monotonous, you don't have a unique inverse, right? Is everyone clear with this? This is a very important, means we have not earlier discussed formally what are the desirable properties as such. So that's what we are looking at right now. And that also forms the basis for discussing about the histogram equalization. So one desirable property first we discussed is the function should be monotonously increasing function, so that the relative relationships, whether it is more or less, how much more and how much less could vary, but the moment your function is monotonously increasing function, if let's say pixel like say one pixel p1 is having intensity i1, pixel p2 is having intensity i2, if i1 is greater than i2, right, then once you apply this transformation, these pixels intensities will be still either equal or greater, but never the relation is reversed. Okay, so suppose if you consider a case like here, suppose one pixel is having this intensity, let's say 100, this is having, let's say 105. The moment you move there, it would be either, if one is more earlier, it will be either more or same, but nevertheless, never it is less. Okay, that is what the important property. Negative, the transformation you don't worry about it, it's just one specific, very specific context, so you take it out of the equation. So that's one important property. The second one we discussed is, suppose you have here once you want to get back the original one while doing this enhancement, so what is then going to happen when it is strictly monotonous versus not strictly monotonous is, there is a unique inverse transformation here. Now if I give you what is the output mapping here, knowing this curve, I could always tell you where it gets mapped to, whereas that is not possible here. Are these 2 points clear to everyone? Or any question or doubt here? Okay, right. Say histogram, I think this you have already answered that earlier in the previous class, but can you make a histogram as a PDF? So let me just come back here before asking this question. You should be having these histogram images somewhere. Yeah. See how we are drawing the histogram. Let's say you have 0 to 255 values. You are counting the number of pixels that have this particular. So how do you, so if you are writing your own program to draw a histogram, what will you do? You go through each, you create an array or a vector of size 256, right? And then what will you do? You go to 1 pixel, you initialize it to 0, you go to 1 pixel. Suppose if that pixel intensity is to, for example, 120. So this being 0 to 255, okay, assume that your indexing of your vector is also starting with 0. Otherwise you just manipulate plus or minus, that -1 or +1 you would be using. So output of, then inside that you got the pixel value, so image of that row comma column, that will give you where it is. So assuming that it is index is starting there is 0, that equal to plus you do, right? That's how you go through the entire all the values. And that's how you get the histogram of this, right? Hope everyone is clear how you could plot histogram other than using the hist command in the MATLAB, right? Now the question is, how can you make this as a PDF? I want to see this histogram as a PDF. So what is all that I have to do once I get this? After I get this?
Find the mean and variance.
No. I give you this. Okay. This hope it is now clear on how you obtain a histogram. Correct? So you got the histogram. I want to treat it as a probability density function.
You have to join the curve.
Divided by the
total number of pixels.
Divided by the
Total number of histogram.
total number.
total number of.
Histogram frequencies.
So what will be that? How do I know?
At each and every location. So histogram that by the total number.
So should I have to now make a summation of going from 0 to 255 and add it, or is there any simple way to know that?
Divided by the maximum.
Divided by the maximum intensity, yeah?
Yes, sir.
Are you sure? It's a very simple question. I think last time some of you have already answered this question. Means it is true that you sum all these things and divide it. I don't want to again do this operation of order of n, where I go through all this 255. Is there any simple? Do I not know the sum without actually summing all those values again?
Number of pixels in the image.
That's it, right? If I have a image of size m by n, m rows and n columns, the sum would be equal to, I have an image of size
m
by
cross n.
Yeah, that's it. M multiplied with n would give me the total number of pixels. So what should I do now? I simply have to divide these values, okay? The whole of this thing, whatever value everywhere I have it. Say for example, I have stored it in a matrix of A. All I have to do is A dot slash or dot divided by. Anyway, dot is also not required because anyway I'm doing with vector operation, but you can keep it for being safe. M multiplied by n in bracket, right? That will give you a probability density function. Is that clear to you all? How do I get probability density function out of a histogram? Right? Hope it is clear to everyone. Now, here I have only 0 to 255. Suppose I am using a integer. Okay, suppose I am using maybe integer. Let's start with simply short. I think okay, short is fine because short is what you would already use. So still, do you remember how many bits will be there in a 32-bit machine for short? We were discussing earlier.
2 raised to the power 32
4
minus.
bit.
Sorry, no. Short, it's not int. See, 32-bit machine means always we say it for an integer, how many bits will be there. In a way, you could think of it that way. Short will be half of that. It is short. It is short by half. So how many bits will be there?
2.
Short will have how many bits per pixel?
16.
16. So what is the maximum value?
2 power
2
16
power
minus
16 minus.
Right, 2 power 16 minus 1. Okay, yeah, 2 power 16 minus 1. What would be that value? Can you quickly do the calculation and tell? I think it will be 64 KB, I think. 2 power
65,535.
Right, correct. So, so if you do 2 power 10, 2 power 10 is 1024, right? Is that correct? 2 power 10 is 1024.
Yes.
So that will be equal to 1 kilobit. 1024 is in terms of bits. That's what we call it as 1 kilobit, right? 2 power 16 means 64 KB, right? 64 KB. So those many values. So yeah, coming back again, you have from 0 to 64 into 102, 64,000. Let's keep for some yes, to keep it simple. 64,000 values are there. Now this drawing this histogram is going to be a very yeah, it's not very informative, right? You see, we wanted an abstraction of the image. The image is, let's say, 256 by 256. Now you made it to 1024 by 1024. So is it, can you somehow make it more meaningful now? How do you make the histogram more meaningful? Is there any way you could make it, do you think still it's an abstraction? See, I might have 100 by 100 image. Now I made a histogram which is bigger than the image number of pixels. So this has become less informative right now. Is there any way you could make it more informative? Any idea on how you could
Sample the
make?
histogram.
What do you mean by sampling the histogram? Can you do better than that? What you mean is perhaps you keep only values of like 1 for every 4 or 5. That's what you mean by sampling, right?
Yes,
Can
sir.
you, yeah, can you come up with something better than that? Can you think of something better than that?
Having a range of values.
Sorry. Other than
Estimating it as a PDF.
see, how do you do that for PDF? Also, you have to come. So, yeah. So histogram usually what we are taking here is 0 first value to L minus 1 we are doing, right? That's now being, if it is 100 by 100 many image, you have 10,000 values. But now your data type is short. So this is blowing up on the x-axis 1020, yeah, 64,000
So
values of.
by binning, we can take bins
Right,
instead.
right. That's correct. Good. So what you would do now rather is take range of intensity values. See, what in a way you are doing when you are using short is you have a lot of values, even finer changes you are capturing. So in other words, the quantization that you are doing is very finer, correct? So if you are taking bins, it only means that the nearest values you will be grouping together. So now assume that you again make 100 bins or something like that. So then any value that falls in this range, let's say 1 to 10 images, you make into one bin. So this is how you would be plotting, particularly in medical imaging. You would never use unsigned character there. You would rather use minimum. You would be using short. Of course, X-ray is slightly different because that you might store it. That too not while capturing, but while you do processing on it, you would be using unsigned char. But otherwise, while storing in all, I guess even when it is stored, it will not be unsigned char. Unsigned char is basically 8 bits. So you have 0 to 255. So that's not how you do it. So,
So,
while you are, yeah. Yes, sir.
so like if we're binning it, are we not losing some of the information corresponding to some pixel intensity values?
See, if we don't want to lose any information, we have to plot from 0 to 24,000 values. So there is no abstraction happening there. We are making it more complicated. We just want to see how the distribution is there. When your values are too high, of course, you would lose something, but that's what, see, the moment you are graded, we are losing a lot of information, is it not? The grade is like we are taking an abstract perspective of your performance and your intelligence. The moment you are tested, you get only samples of what you are. You will never get yeah, so there is no way you could exactly do it. But this would more or less, what you are doing is the best way that you could think of is you do the see, basically nearby values, when your quantization level comes down, they all gets grouped together. And also when you are taking a look at the image also, what would happen is nearby values, that too when there is such a big range, would almost visually as well as from your algorithm point of view would all fall into one category, right? Even assume that although this image itself, you see the Einstein in this image, although there are 256 values, we won't really see their 256 values for distinction. Still, we make a very good sense of that image, is it not? So the same way, that's why you have to be careful while choosing the size of the bin. Of course, it again comes to the quantization effects. If you just consider a so this is a trade-off, while how much distinction you could take versus how much abstraction you want to bring. Is it not?
Yes.
Right. So
Sir, can't we use histogram equalization to
yeah,
a shorter number of bits?
see, even if you are doing histogram, well, see, the moment you have such a yeah, it's a good point what you are saying is, but still once you have such a big numbers, the histogram equalization also doesn't make you a very good sense there. Probably, see, you might not want it at that level of precision also for doing it all the time.
No, sir, I'm asking we can reduce the bits per pixel variable, no, sir.
Bits per pixel variable.
That 2 power bits per pixel minus 1 is there, right? So
right. See, if our requirement is just to reduce the bits per pixel, that's a very simple problem. You so if you recollect the last one, histogram stretching, where I have it here, so let me open that. See, casting it to 0 to 255 is literally nothing. You can do that all the time. Say for example, where do I have it? Not in this PDF, so that should be there in the 10th one, right? Yeah, all I need to do is this simple one is good enough. If I have to do it, what I would do now is you take f max and f min to be 0 and let's say 2 power 16 minus 1. Then this would bring it to 0 to 1. Then you multiply it with 255. That would give you in bit 0 to 255. See, this casting, you keep on doing it. So if the objective is to just to bring them into this is something you could do there. That's not a problem. But it's not exactly this. We still want to keep the same data type, but just to get an abstraction, and then it's at the bins level you are going to do it. See, after the construction of the histogram, in fact, you could then, if you want, you could do on top of it histogram equalization. That's what, in fact, what is done. And then when you are coming back from there, you know, for example, that then how the way you look at it is 10th bin got mapped to, let's say, 12th bin. Okay, some of you might not understand at this point histogram equalization. We'll come to that in the next class. But anyway, since he is very clear with that, I just giving histogram equalization is one. You want to equalize the histogram, you are applying some transformation. That's the idea. Okay, so this you could apply even on a histogram that is obtained where you are using bins instead of intensities. That's what in fact you will be doing.
Okay, sir.
Yeah.
Sir,
Yes.
sir, in image compression algorithms, like if we want to compress the image, so that also does the same thing, right? Like it reduces the storage, like how the
No.
the
See
storage
again,
capacity of the
yeah.
image.
See, there are different ways there actually.
Lossless and lossy
Yeah,
compression.
lossless compression, if it is there, that's a different. And again, the way it is done is also slightly different. For example, you find out a discrete cosine transform. That's the most commonly used one for the compression one, where you have all these values, okay? And on that, you want to find out a combination of sines and cosines with that harmonics, and then you go until there is not much of an error and something like that. It's slightly different. And
Okay,
if you
sir.
are if you are doing lossless compression, then you won't be using the DCT which we are mentioning. Then it has a different set of methods to compress the values in a different way. There are different ways of encoding, and all other things come into picture there.
Okay, sir.
Yeah. Any other question? Is that clear? What we do with means when the values are high, using a bin, then getting a PDF out of it.
Sir, that means using bins is a kind of segmentation also. We can say that, right?
See,
Suppose if we to use only 3 bins, then we can segment the picture into 3 levels of intensity.
See, it may incidentally or accidentally give you that, but again, if your value is falling into 2 bins, say assume that your image is there from for example 100 to 150. The way you are doing, part of it may go to one and the other may go to the other. Okay, see, I would slightly rephrase what you said. Histogram equalization and histogram based operations is a very common pre-processing step before you do segmentation. Then on top of it, you will be doing something else. This is quite common. You are almost coming close to segmentation, but you need to do more on that. You won't usually do simply based on the intensities. You might use some edge information there, or then you would do something else on top of it, or some region characteristics you would be looking particularly after doing histogram equalization. That's what you would be doing. See, histogram may give you in some trivial cases direct segmentation. For example, the kind of problem you were doing earlier, like for example, if you have all intensity distinction is very clear, like from image to a normal image to segmentations. If you are doing on a paper on which some written text is there and you are doing there, you might almost, this itself might be good enough to get their segmentations. But in you could get that. But for example, if you have something like this won't give you. Most of the time I want to get the head of Einstein here. Those cases you will not simply get with with histogram itself. I could do some histogram equalization on top of it. I need to look at the gradient information or something like that. Is that clear? Yeah, good. Okay, so any other questions so far? So let me, anyway, this I'm not going into the detail anymore now. This anyway you have looked in. Okay, somehow I could not see the mouse is okay. This is not coming here. Let me put it here. Okay, yeah, maybe it's in which mode, I don't know. Okay, now I could see. So again, this formula is very clear to everyone, I think. Like, this is just a linear equation that we are doing. F of x is so any I think the explanation is clear in the video, I hope. So I don't want to just repeat that anymore. Yeah.
I have 2 questions on the transforms intensity.
Which transform?
Can you show me that graph, sir, where you showed the logarithmic and power transform?
I think that's another this one, right? Yeah, 1 minute. This one, right, Arvind?
Yes, sir. Yes.
Yes.
This one. So, one basic question, like how is it still staying in that range of 0 to 255 even after applying log and power and all?
Okay. Yeah. It's a good point. So anyone would like to answer that?
Scaling.
That's all. You do scaling. So that's why you have it seen, for example, the gamma transformation, you have C here. The C should take care of that. You take the maximum value you are getting out of it. You normalize with the maximum value. Then you multiply with the C, for example, which could be, let's say, 255.
Okay.
Yeah. What is the another question?
Another one is in the same graph. Can you show me? Yes. Yes. Will log graph will always be more than the nth root?
Log is always more than nth root. No, not necessary. See, it is just one we have drawn. So if you look at here, for example, the next one, if you are going to see here, it could go something like this also. See, for one reason, we normally don't use the log graph. The reason being, you don't have too much of a control over the how the curve would come like. See, for example, assume that my object of interest, which I want to enhance, or let me put it a slightly different way. For example, in the histogram, whole thing got concentrated around here. Okay. So it is in this region I would like to stretch more. But when it comes to the log curve, I can't really do much with it. It's already fixed. On the contrary, when I take r to the power of gamma, I could consider by varying gamma, I would get different curves now. I could visually see now and can go ahead with that value of gamma, which is fitting my bill well. Whereas with the logarithmic transform, I don't have that freedom there. And for the first question, the see for for very small values of gamma, okay. Anyway, this is like nth root where n was an integer, so you could think of it something like that. But that would somewhere be here only in the middle. It will not like you could find out gamma curves well before and after that as well by varying the gamma value. Right, good. Okay. So now I want to put you a question for which I'm still like trying to get the answer, or I'm still exploring it, but hopefully you could also try your own. Okay. Is like, I'll come to the derivation of, this is part of that histogram equalization. This is again very basic thing. You all know the PDF and CDF, right? Probability, you have studied it. So assume that I have a probability density function, and then I compute CDF out of it. Okay. This is again, now I am talking in the continuous domain. Okay. Continuous where my R is a continuous. Assume that forget about the intensities. Now assume for time being this R is a continuous variable. So I have a PDF here. I constructed a PDF. So what is all the property that is there now when I say this is a PDF? The sum should, yeah, if I integrate from 0 to L minus 1 or R, it would give me 1, correct? So now I compute a CDF of it, right? So what will I do? How do I compute CDF of it? Suppose I want to compute the CDF value at, let's say, R equal to R naught. What will I do now? You are given this
integration from 0 to R.
Right, correct. Integration from 0 to R, PR of R, dr. That's what I will do. That would give me. Okay. So assume that I have computed a CDF of it. Will the CDF be still PDF? That's what it looks like. I will check with some book and I'll think about it a bit more. But meanwhile, I'm just asking you as well. I don't know the answer at the, I don't know the answer definitely at this point, but since you have studied some probability theory and all, I want to check with you guys. Is it still a PDF? What you get there?
No,
No,
sir.
No, sir.
No, sir.
no.
CDF will be from ranging from 0 to 1, right? It will start
Uh,
initially from 0 and it will be a monotonous function actually. It
yeah.
won't
So
decrease at all.
suppose if I
At the
tell
last
you
value,
some
it will be equal to
properties
1.
also, now I would
Yes, sir.
slightly, if I tell you that this is a monotonically increasing function, okay?
Yeah.
Then what would happen? Will the under what conditions a CDF will be a PDF? That's what I would like to know. This is for a continuous case, not for a, of course, discrete case. Forget about the discrete case. I'd like to see, yeah, if somebody could answer next class, it would be great. So under what conditions I have a PDF of a continuous variable that from the PDF of that I'm constructing a CDF by integrating. For example, I want it at R0, I integrate from 0 to R0 and put it. Under what conditions this CDF will be still a PDF? Should it be
So it
If
is
not
PDF
the
is impulse function, then it's PDF equal to CDF.
CDF? That it's a clear result that is already discussed in your courses or something like that.
No, on any other function, if you will integrate, then that CDF at the end we will get 1. But in impulse function, we will integrate only that simple
Yeah. Okay, so I still
area.
am trying to get the intuition for it. It's not, it looks like if you should not look at it in the discrete domain, I think. Discrete domain, yeah, what you said is
Sir,
what
when it's
exactly the
strictly
result here.
monotone,
So very likely that's the right one, but still you think about it. Okay, don't take that answer for granted. That's exactly what has been told here. You take a strictly monotonically increasing function where you have an inverse mapping. Okay, and then if you are computing the CDF of that function, that would
look
be, in
similar.
fact, again, it will have the same properties as the PDF, but now what you would get is a uniformly distributed PDF. That's what you would be getting here. It is if you look at it, yeah.
Can you
Anyone?
repeat again?
Okay, I have a function which is a strictly monotonically increasing function. Okay, yeah, something like this, right? Now for this function, I compute a CDF. That CDF is another PDF. It's not exactly the original PDF, but it would give you another, it has all the properties of a probability density function. As
So does the area under the curve equal to 1 condition also hold there?
yes, that's right. In the continuous time domain, that's something counterintuitive if you think about it in the discrete domain. So you should look at it in the in the continuous domain only. Think about it. Since my fundamentals have been weak in probability earlier, so I should teach the subject again, then only I will read it in detail. So before that, you don't wait till then, you try to analyze it for yourself. So and what you would get as a PDF now is a uniformly distributed PDF. Samir, is that correct? Is this going to happen from what you see?
Yes, sir.
Okay, so the rest, yeah,
So
again,
actually, yeah, actually it is correct, sir.
yeah, okay,
Like if we consider
yeah. Don't try to
a
answer it
terminated
at this
sigmoid
point.
function.
Yeah, no, and don't try to answer it at this point, everyone. So please think about it. And again, you all have done probability and random variables, all the related math course. So you have no excuse to not to think about it. So please go ahead. I'll also also don't just stop with some mathematical equation giving you that answer. Just try to get some intuition also, because the counterintuition for me, it looks counterintuitive if you look at it in the discrete time domain, because see, there is values, sum is giving you the 1, but again I am summing it up, but still I would get 1. So again, there is definitely a wrong, there is a fault in the logic. Okay, it's not the right logic, but think about it. So this is in fact what is done in the histogram equalization. This is all that is done in histogram equalization is you take a PDF of it, anywhere you want the value, you sum the values, and of course you do something else. We will come to that anyway in detail in the next video. But this is something I want you to think about it. Yeah, any quick explanation you could, Samir, Sumant, you could say.
So actually, like I just worked out, if we take a, sigmoid function, something like sigmoid, a terminated sigmoid,
Okay.
then it will give the PDF like this only, like it will be uniform.
Right. It should be true for any strictly monotonously increasing function. So yeah, if somebody could clearly tell me next time, that would be great. Not just for one function, but intuitively also I need, when I am trying a fresh without any background in probability, this looks counterintuitive, but yeah, think about it. Anyone else would like to comment on that? Okay, so how much time?
So what is plotting the CDF means? Like from we are taking a fraction of some part of a PDF, and again we are plotting it, so that gives us a PDF.
Right. See, CDF of a PDF is still PDF in one way, if I want to say, given that there are certain conditions satisfied by this PDF. That's what the argument we are saying here.
Yeah, although we can show, like the representation could be like as it's seen in the figure, it seems like a PDF only, the area under the curve being one and
correct. That's right.
Maintaining constant.
Yeah,
so
that's true. Okay, so yeah, I think with that, next class we will discuss about the histogram equalization. So this anyway, that time we will discuss about this in more detail. So how much time is left for us? Let me just, I think I won't be, I could not see. Yeah, I think we are almost done. So let me stop sharing here. Okay, 9:45. You have 5 more minutes actually. So anyone have any other thoughts to share?
You won't represent each pixel in shots, sir. Means I didn't get what is going on.
Okay. See, for example, I have assumed. So your question is, how do you make bins and how do you create the histogram? Correct?
Yes.
Say, for example, let's take to make things simple. Let's assume that I have intensity range is 0 to 1000. I have one image using, I have stored it with chart, and then I realized that just because I am storing it with chart, while constructing my histogram, I won't be taking 0 to 2 power 16 minus 1. Rather, what I would be doing as a first step is I would be looking at what is the maximum intensity I have in the given image. Assume that I have the maximum image to be 1000, right? So then what I would do is, for example, I want to construct bins, 100 bins are good enough for me. So each bin would come now roughly to, to make things simple, last one you take 999, or otherwise also doesn't matter, 101 bins, for example. Okay, so 0 to 9, one bin, 10 to 19, another bin, 20 to 29, another bin. So this is how I make, let's say here 100 or 101 bins. And then I go through the image and assume that at a given pixel, I got an intensity of 34. So which is the bin value that I need to increment now?
Fourth bin.
Yeah, fourth or maybe third. You are right, probably it is fourth or third. You just need to check with 0 and other things. So that bin value, now you will increment it. And that's how you go through the whole image and you have now the histogram.
So you means we basically convert this into pixels of 0 to 100.
Don't say it that way. We are just grouping the pixels from within the range of 10. Okay, again, other side you don't consider. But for example, we treat anything from 10 to 19 as just one single value. That is how we are treating it.
Okay. Yes.
Yeah.
Yes.
Good.
Sir,
yes.
So the binning concept here in the histogram equalization part, like, is it similar to what we have seen in HOG, like computation of HOG?
Yeah, you could, yeah, histogram there, that's also is histogram, exactly the same. Histogram of gradients also, if you start taking all the values of gradient, it ends up nowhere, correct? At least the consolation here is you have only integer values when it comes to pixel intensities. And when it comes to the gradients in histogram of gradients that we studied in computer vision, the gradient you are calculating based on the, for example, ix minus I1, and then it could end up even the way you are based on the way you are calculating the gradient, even non-integer values also, or the angle, for example, angle histogram of orientation of gradients. So the orientation could be like tan inverse y by x is what you would take there. So with that, you could even end up with values that are non-integer values. So what you would be then doing is, for example, 0 to 45 one bin, it's exactly the same. There you are using the histogram. See, this histogram need not necessarily be always for an image also. Even if you want to take a look at how the sales of a particular product have been changing over time, then what you would do is over 1 week you would be seeing how it is there. So in that case, your binning is, if you won't take it in days, but you take first 7 days in one bin, second 7 days in one bin. You want to see it at a more higher level, maybe every month you would be seeing. So that's also in a way a histogram. Is that clear? So basically you are looking at the frequency for each of those variables, which could be, for example, a grouped one instead of an individual one. Okay, so if there are no other any other quick questions?
Sir, can you share the reference material for that particular topic at the end of the video, sir?
Okay, yeah, see, for the spatial domain analysis, image enhancement in the spatial domain, if you want the reference, this I have taken from image processing using MATLAB. What is that book? Anyone can quickly remember that? Image processing, Gonzalez and Woods. Okay, image processing using MATLAB book, Gonzalez and Woods. Then the others I myself taking from different like different sources. There is no single source, but at least for image enhancements in the spatial domain, frequency domain partly, then I have my own way of I took from multiple and then had my own material there. So that I would be Gonzalez and Woods will be a good reference for you for these two topics at least. Okay, the first introductory, there is no single textbook as such because this is again everybody has their own flavor and version of these things. So me also I'm taking from different sources as well as adding a bit of my own material as well. That's why anyway you have the video part is there. I'm uploading the slides also. Then these are the books where you will find mostly the material.
Okay.
Yeah. Any other?
Sir, what is the exact reason for binning, sir?
Yeah, see, the very reason we are doing histogram is to get an abstraction, correct? If you are not doing binning and taking the whole all values, see, you might not do binning for 0 to 255 image, but medical images having chart and all, as we have seen, plotting it 1000 values plotting, and you would see nothing there. It's almost like looking at numbers. There is no abstraction you are getting there. There is no interpretation that you could make when you have so many values. Okay, the way you would like to interpret, or even practically also a slight variations, that it's like I am fine with one decimal, for example, while interpreting the numbers. I don't want 1.23456 8 10 and going on and on, which is actually more precise. But sometimes it's not the precision I want. It's more the interpretation or inference from those numbers is more important for us. So that is why you do the binning.
Okay, sir.
Does that answer the question?
Yes, sir. Yes, sir.
Okay, good. Yeah, any other?
So we are doing this for visualization purpose.
No, not just visualization. You would see shortly what we would be doing with, see, histograms. Right now we are going to study it in terms of image enhancement. Okay, so in that aspect we are taking a look at right now. But again, with the excuse of image enhancements, we are now studying all these methods. This again, as for example, Muhammad is using earlier it for segmentation. When you have a scanned document, from that you would like to extract the text from it, he was using histogram based approaches there. So you would see its applications in various other operations that you are going to do. For example, segmentation you could use. And irrespective of these operations, most of the times this is at least used as a pre-processing step. Okay, not in all cases, but there are quite a lot of cases. You have an image, you want to process it and make some inference. Even you want to, before you give it to your network also, even if you are doing deep learning based thing, you usually do histogram equalization of the image and then give it, because that takes care of contrast and other things. Again, it's not like histogram equalization is not always the one to go, but there are quite a good number of cases where if you do histogram equalization, then as a pre-processing, then followed up by your edge detection or segmentation or region based characteristics, whatever it is, or some tracking part, it would make a better sense there. So it's not just visualization. This is used, for example, it can be used in segmentation, and more importantly, as a pre-processing step for many of the algorithms.
Yes, sir.
Okay, good. Any other question? Okay, then we will wrap it up here for now. Let's sign out and then see you again on Monday. Meanwhile, I'll send the histogram equalization video and then we will discuss it further in the class, on Monday's class. Okay, yeah, bye.